Hi, I'm James Eastham, a developer advocate here at Datadog, and in this video you're going to learn why distributed tracing should be the first thing you think of when you think about observability in asynchronous systems. And yes, for all you developers listening, that means you need to forget about console.log. When you think about asynchronous communication, as you learned in the last video, you've got a producer, you've got some kind of consumer, and you've got some kind of message channel in the middle. The producer is going to send a message onto the message channel, and then you've got a consumer consuming that message. And remember, if you're doing publish, subscribe style communication, you may have n number of subscribers all consuming that same message. This setup, whilst it does reduce runtime and temporal coupling, and remember, runtime and temporal coupling is the coupling that at the point in time a service is running, another system that it needs to communicate with also needs to be running at that moment in time. Prioritizing this asynchronous communication where you've got this transport layer in the middle really reduces that runtime and temporal coupling. It does make understanding cause and effect incredibly difficult, because understanding that as a developer of this service here, maybe this is the orders service, understanding that actually you've got these 4 downstream systems that are all really dependent on you, not making breaking changes or not stopping publishing events or changing how you do things. They are all dependent on you. And equally, as a developer of one of these downstream systems here, you also are dependent on the order service back up here, albeit through the proxy of the message channel. You need to understand what is happening, who is upstream of you that causes your system to need to do some work. And equally, as a developer of this service, you might publish your message onto its own message channel, which then also needs some downstream system to do some work. This, of course, makes debugging really difficult across your entire system. But if we just zoom in a little bit, imagine you're this developer on the orders service, and the orders service as a whole is made up of a few different subsystems. The orders service has some kind of API layer. That's the API layer that any customers, any users are going to interact with when they try and place orders. But your orders service is also made up of a few different subsystems. There are some subsystems in here that maybe the communication inside your orders service is also asynchronous. Maybe you have message channels here. So for example, this user is going to come along and try and create an order. The API is going to receive that request, validate that request, and maybe the API just posts that message onto some kind of internal queue. This is a point-to-point style of integration. And maybe this service down here, this subsystem, is going to pick up their messages from that queue and do some work to do the initial processing of an order. Inside your service boundary, asynchronous communication is still really useful because it allows you to make things more loosely coupled. It allows your subsystems to scale more independently. It allows you to deal with load in a more resilient, in a more robust way. But you've still got asynchronous communication, which means those same problems with observability, those same problems with understanding cause and effect still apply here at this slightly more zoomed in level. Now, I know what you're all thinking. Your console.log, your console.writeline, your log statements have got you this far. Why should you start caring about distributed tracing now? Because logging is all you've ever done. Logging is all you've ever known. And logs are wonderful. Doing logging is better than doing nothing. And it's a very big but, when it comes to building distributed systems where you've got disparate components that are all communicating together and working together at this large scale to get meaningful work done, understanding how requests move around the system, understanding how components relate to each other is vital. And logging, whilst incredibly useful in certain scenarios, does not give you that cause and effect, does not give you that causation to see that this thing happened in this service, which then caused this thing to happen down in this service over here. Logging simply does not give you that. So when you're dealing with complex environments, complex distributed systems, distributed tracing is incredibly important. A log gives you a single point in time look at that specific thing that you wrote in the code to log that statement at that exact moment of execution. A trace gives you context. And let's just settle on some terminology just for a second. At the very top level, the end-to-end flow of a request is a trace. You've got a trace here for a post request that was received to your orders service. A trace can then be made up of lots and lots of individual spans. So here there's a span underneath that for making a call to Amazon Step Functions. There's a span underneath that for the actual workflow processing. So you've got a trace, which is the overarching flow of a request, and you can have lots and lots of different spans inside a trace. These spans can also span lots of different multiple distributed systems. You can see this is actually quite a big trace. There's lots and lots of spans. There's lots and lots of other things going along inside here. Traces and spans can also have attributes. And this, when I say distributed tracing is incredibly important in distributed systems, that is tracing with lots and lots of additional context. It is context that really starts to add the power to these requests. And you'll see underneath here, I've got lots and lots of attributes for this trace. This happens to be a trace that responded to a HTTP request. So you're capturing things like the HTTP method, the status code, the URL that was actually hit to invoke this request. This service happens to communicate with DynamoDB under the hood. So you're capturing the read units and the write units that DynamoDB used for this request. And that's all technical context. That's all context that any system that is doing HTTP communication and interacting with DynamoDB should care about these kind of things: the HTTP route, the HTTP method, the response code, the read units, the write units. But then you also can add business context. You'll notice here that I've actually also got attributes in this span for the order ID, the number of products on the order, the user ID, the type of user that created this order. And this business context gets really useful because then it then allows you to filter all of your telemetry by that user ID. I can come back up here, I can filter by user ID, and I can now see all of the telemetry related to that specific user. And I can see that this user has interacted with the order service, it's interacted with the user service, and also the activity service downstream. So you can start to filter and look at your telemetry in really interesting ways. Also, importantly, always understanding cause and effect, always understanding how the different parts of your system relate to each other. This end-to-end trace view works because of a thing called trace propagation. Trace propagation is simply the act of taking the trace in one system and propagating that down to different downstream systems. So whenever you send a message to a downstream system, however you are sending that message, you will also include the context of the trace from your system. That means when that downstream system receives that message, whether that be over HTTP, whether that be over a message on a message channel, they have the ability to then propagate that trace context. Now, if you're using Datadog and the Datadog tracers, for most of the common messaging frameworks I've ever come across, whether you're using Amazon SQS, you're using Kafka, you're using RabbitMQ, trace context will be automatically propagated whenever you make an API call. If you're building with .NET and you send a message to SQS using the AWS SDK, the trace context will automatically be injected into that message you send. But that's not always something that will be possible. So to give you an example of how this might work, here is a code example for a message that's being sent to Amazon EventBridge. It largely doesn't matter what the programming language is or what the message transport is in this scenario. And when I create my event that I'm going to send, I'm using the cloud event specification here, which there'll be a video on later in the series. When I add all of my information about my event, I also set this trace parent property. And I set that trace parent property to the current trace parent. What this toTrace parent method call gives you is it just creates a string that matches the W3C trace context, which is this lovely looking thing just here. And this W3C trace context is made up of a few different components. First, you have the version. This is the version of the trace context. There's only one version at the minute, so it's just version 0. Then you've got the actual trace ID. Remember, the trace is the overarching end-to-end request. You've then got the span ID. That's the specific span inside that trace that it relates to. And then you've got some flags on the end for saying sampling, or one here indicates that this trace will be sampled. So now, whenever we send this message in our code, we're always including the trace parent in the actual body of the message that gets sent. And the same applies at consumer side as well. There is a way to do manual trace extraction. I'll put some links in the description below for how exactly to do that. Same applies if you're building with OpenTelemetry. OpenTelemetry also has a whole bunch of automatic trace injection and extraction, depending on which programming language you're using with OpenTelemetry. But if you do need to manually inject and extract trace context, there's some really good examples on the OpenTelemetry documentation site for how exactly to do that. You can see here from an injection perspective, you're creating this carrier, which simply has the trace parent and the trace state. And you use this propagation and call inject to inject the current trace context, that is the current active span, into the carrier. That's then going to populate this instance of the carrier object with the current trace parent and the trace state. And the same applies at an extraction level. If you are extracting a trace in a consumer, you've got your carrier interface again with the trace parent and the trace state. You create a new instance of your carrier, then you call propagation.extract. You extract that into the current active context with the input being the carrier string up there. Now, at first glance, this might seem like a silver bullet. This might seem like now you've got the ability to fully understand cause and effect, to fully understand how the different parts of your system relate to each other. And if you're using either Datadog or OpenTelemetry, you get an element of this for free in the automatic trace injection and automatic trace extraction is something that is supported by some of these languages with some of the messaging frameworks there. And if the runtime or messaging layer you're using doesn't support it, you've got the escape hatch to be able to manually extract and inject. But as you saw a little bit earlier in this video, this can actually sometimes cause slightly more confusion. Because if you are a developer on the orders service and you're interested in just your service and just your service's subsystems, if you come back to this trace you had a look at earlier and we zoom this all the way out, you can see actually this trace is a 4 minutes and 24 second trace. For whatever reason, this trace is now incredibly long, and it's incredibly long because there's a few different services here. You've got the activity service, which is a service that you're not concerned with. It's another system, it's another team, it's not your responsibility. You've then got your order service, and then you've actually got some work for the inventory service as well. The inventory service is also included in this trace. So you've got this really long 4 minute trace when actually your API request, the call to the orders service, the service that you cared about, should be completed in about 41 milliseconds. So if you were to start analyzing your trace data now and look at the trace around the post orders, the post request to your orders API, it may skew the data because you've got these traces that are 4 minute long traces when actually you only care about 40 milliseconds of it. And not least, if you're a developer coming to look at this and you come in and have a look at this trace, we have a look at the span list, or we have a look at the waterfall view, you see that you've got an awful lot of additional context in here that isn't actually relevant to you as a developer of the orders service. So whilst trace propagation is incredibly useful, particularly if you're using parent and child traces, whenever you get a trace in a downstream system, you're parenting that to the upstream producing trace. Whilst that can be useful, it does cause its challenges, it does have its trade-offs. So what's the alternative, I hear you ask? And that's what you're going to learn about in the next video in this series. How span linking as an alternative to trace propagation can help solve some of these challenges with parent-child trace relationships, and actually when you should choose to use span links and when you should choose to use trace propagation. If you don't want to miss that video, make sure you hit the subscribe button underneath this video. That ensures that you don't miss the next video in this series of observability and asynchronous systems, and I'll see you all in the next one.